Friends, welcome to my YouTube channel. Dhanesh here. See, last video we were discussing with speech recognition systems. Today, I am going to discuss about the mathematics behind speech recognition systems and the Fourier transform. Let's start. See, we discussed most of the aspects we discussed related to ASR systems, automated speech recognition systems. As you know, ASR systems accurately translate spoken utterances into text, words, syllables, etc. Some of the examples for ASR systems are YouTube closed captioning, voicemail transcription, diction systems, Siri front end, etc. These are all ASR systems. And the architecture of ASR systems also we discussed in the last video. Speech waveform is the input, and here the output is the pros and different modules. All these modules we discussed in detail in the last video. You can watch that video. It's okay, even though if you are not for this math, those modules are not that much important, but I'm just telling, for an ASR system these are all the important modules you need to understand. One is the pronunciation model, acoustic analysis, acoustic features, acoustic model, language model, and the main important part, a decoder. So these are all the modules that's come into picture for an ASR system. For to understand the mathematics behind this speech recognition, we need only one module, that is acoustic analysis. And even we discussed in the last video, in the acoustic analysis, in that module, what's happening here, the raw speech signal are converted into discrete sample. It is converted into discrete sample. Each of the sample is in the order of 10 to 25 milliseconds of speech. We discussed these things. These samples are known as speech frames. It's very important. These samples are known as speech frames. This is very important. It is assumed that within each of these frames, the speech signal is stationary and features can be extracted. Now, the next module, acoustic features. The features are extracted from the discrete sample, that is speech frames. Here a lot of signal processing is involved. It is motivated by how our ears work. So what is the mathematics? What is the signal processing involved here? We are going to discuss about that. And before that, I'm just telling you some idea about acoustic model as well. Acoustic model creates the basic unit of phoneme from feature. You may be familiar of phoneme. Phoneme is a discrete and distinctive unit of languages that can be used to differentiate between words. Most language has 20 to 60 phonemes. We are using hidden Markov models such as HMM as acoustic models. HMM as acoustic models. Currently, we use deep neural nets as acoustic models. Most probably, we are using RNNs, recurrent neural networks. We use recurrent neural networks for convoluted neural network. It cannot handle sequential data. That's why we are coming up with recurrent neural networks, LSTMs can handle the vanishing and exploding gradient. That's why most of the acoustic model LSTMs also we use. So now we are getting into, see, how we usually read audio files. Audio files, we are using a Python library known as LIBROSA. LIBROSA is a Python library that is very effective while working on audio files. You can install by using the command pip install libros. It's LIBROSA. Sorry, it is A is there. Pip install LIBROSA. If you have Anaconda in your system, if you are using Anaconda, you can use this command conda install -c conda -forge librosa. This librosa is a very effective library for handling audio files. How we can load these audio files using librosa? You can use the command librosa.load. This function returns two things: an array of amplitude and sampling rate. One is an array of amplitude and sampling rate. See, some of the aspects where here we are discussing with signals or waves. I am telling you some of the most fundamental things about waves. This is a wave. This is a wave. This is known as amplitude. This is amplitude. This distance, this is the amplitude, is the maximum vibration of the medium particles from the mean position. That maximum vibration we call it as amplitude. And you know, this distance we call it as the wavelength. This is the length of the wavelength. And the time for one rotation, a complete rotation, we call it as the time period. It is known as period. It is the time for one rotation. It is starting from here and ends here. How much time it will take, that is represented by t, time period. These are all the basic concepts of a wave. And the reciprocal of period, time period, is known as frequency of the wave. The reciprocal of time period is known as frequency. You may be familiar. Another term related with wave is the angular frequency. We call it as omega. Omega is equal to the one equation you can write it as omega is equal to 2 pi into f. 2 pi f. This is the equation. Omega is equal to 2 pi f. F is the frequency. This omega is known as the angular frequency. These are all some fundamental concepts related to wave. So this function, as I told, when we do librosa.load function, the function returns two things: an array of amplitude and sampling rate. Sampling rate, for example, if I am telling it is 16,000, it refers to the sampling frequency used while recording the audio file. Sampling rate is the sampling frequency. It refers to the sampling frequency used while recording the audio file. That means this much amplitude, 16,000 waves per second. That is sampling frequency. As I told, frequency is the number of waves per second. 16k, sampling frequency 16k means in 1 second you are getting 16,000 waves. That we call it as the sampling frequency or sampling rate. To visualize the signal, librosa.display.waveplot can be used. These plots represent the amplitude of the signals. So anyway, LIBROSA is an important library to understand the audio signals in speech recognition. This is the visualization of an audio signal in the time domain. See, there are two types of domains. One is the time domain and the frequency domain. The time domain representation of the signal represents the amplitude. Amplitude means loudness. As the amplitude increases, the loudness increases. To understand an audio signal, it is to be transformed into frequency domain. It is very important. To understand an audio signal, you need to transform it into frequency domain, because when you talk about a wave or a signal, its important characteristics is its frequency and wavelength, lambda or wavelength. To understand a wave completely, you need to understand the frequency and the wavelength. For example, a high frequency wave means it's a high energy wave. For example, for a specific wave, when I am talking about ultraviolet, it's a specific frequency, it's having a specific frequency and wavelength. So the characteristics of a wave is determined by its frequency. So to understand an audio signal completely, we need to transform the time domain into frequency domain. Here, our Fourier transform comes into picture. Fourier transform is a mathematics concept that can convert a continuous signal from time domain to frequency domain. To convert a continuous signal, not a discrete signal. Fourier transform can convert a continuous signal from time domain to frequency domain. It cannot convert a discrete signal. See, Fourier transform. An audio signal is a complex signal composed of multiple single frequency sound waves. When you talk about an audio signal, it consists of, lot of complex small signals, multiple signals of single frequency sound waves. Fourier transform is a mathematical process that can decompose a signal into its constituent frequencies. There is inverse Fourier transform is also there. You may be familiar with these mathematical concepts. These are all very important from a machine learning perspective. Inverse Fourier transform is the opposite of Fourier transform. It takes the frequency domain and create the original signal. See, Fourier transform takes the time domain. The function of it is a function of t, and it converts into frequency domain. It is omega. Omega is equal to 2 pi f. So Fourier transform converts time domain into frequency domain. Inverse Fourier transform converts frequency domain into time domain. That is the inverse Fourier transform. See, we need to get into another algorithm, fast Fourier transform algorithm or FFT. FFT, the importance of FFT is fast Fourier transform is an algorithm that computes the discrete Fourier transform of a sequence or its inverse. See, I told when we discuss about Fourier transform, it can work only on continuous signals. But what about discrete signals? So there we need to introduce the fast Fourier transform. It's Fourier. It is not correct. It is I. Fast Fourier transform. Fast Fourier transform and its inverse also we can calculate. See, Fourier transform takes a continuous signal as input, and fast Fourier transform takes a discrete value as input. So the input to fast Fourier transform is a discrete value. Fourier transform, it is a continuous signal. Fast Fourier transform algorithm converts time domain discrete signal into frequency domain discrete signal. These are all the important equations, very important equations for Fourier transform. Joseph Fourier is a French mathematician who introduced Fourier transform. Let us take a function. See, this is our function g of t. The Fourier transform of that function f of g of t, that I am taking it as capital G of t. You can assume it as the Fourier transform of this function. You can take it as capital G of t. Capital G of f, because it becomes a function of frequency. See, this is the important concept. You have a function g of t. Its Fourier transform, it is capital G of f, because when you take Fourier transform, the time domain is converted into frequency domain. So f of Fourier transform of g of t is equal to capital G of f. This is the formula you need to apply. Integral of minus infinity to plus infinity g of t e raised to minus I omega t dt. Omega is the angular frequency. I told you omega, the formula for omega is 2 pi f, or you can write it as 2 pi by t as well, because frequency is the reciprocal of time period. So this is the equation, g of t into e raised to minus I omega t. I is the imaginary number, root of minus 1 is I, it is a complex number, minus I omega t dt. To calculate the inverse Fourier transform, f inverse of g of f, it is, again you will get g of t. It is minus infinity to plus infinity. You need to take the inverse g of f. Then e raised to plus I into omega, we need to write it as 2 pi f, because it is in the frequency domain. 2 pi f t, then df. Here, the integration is for frequency, df. So these two are two beautiful equations for Fourier transform. So you can learn it. This is a very important equation, and it's a really interesting to learn. So that is the converting from time domain to frequency domain, and again going back from frequency domain to time domain. These are all the equations for Fourier transform. But what is the disadvantage of even this FFT algorithm? Fast Fourier transform algorithm is having a disadvantage. When we apply FFT algorithm to an audio signal, it gives us only frequency values, but we lose the track of time information. The track of time, right? That is very important. When we talk, what is the track of time information? That is really important. We lose that. We will get, the frequency domain informations, but the track of time is lost. So we need to find a different way to calculate features which has frequency values along with time. Here, the importance of spectrogram comes into picture. Spectrogram. What is spectrogram? Spectrogram is a visual representation of the spectrum of frequencies of a signal as it varies with time. When applied to an audio signal, spectrograms are sometimes called sonograms or voice prints or voice grams. All this, when it comes to audio signal, we call these terms as well. In a spectrogram, one axis represents the time, the second axis represents frequencies, and the colors represents the amplitude. By using the LIBROSA library, you can write simple Python code to generate spectrograms, to show the frequency domain of that audio signal, the time domain of the audio signal. See that library we discussed, LIBROSA, that is really important. You can do a pip install. You can get that library, Python library, and you can write simple programs for speech recognition, using those LIBROSA library. We have one program written in Python in the playlist that converts audio signal into uh, you know we have taken a audio file, and it is converted into text. So you can see that program as well. It is written in Python by using the speech recognition library, speech recognition package. There you have different methods like listen, record. We used record and listen methods to do that. Fine. That's all for the mathematics behind the speech recognition. Thanks for watching. Please like, share, and subscribe. Thanks a lot.